Hello everybody and welcome to Nuclear Physics Lesson 7. Now if you haven't already finished the electric field topic, please make sure that you go away and watch all of those videos first, because some of the knowledge from that topic we're going to be bringing over into this lesson. In this lesson then we're going to be looking at the next stages of Rutherford's experiment. Once Rutherford had come up with his new nuclear model, rejected the plum pudding model and brought in his basic atomic model, the next thing he tried to do was to measure how big the nuclei of gold were. Now in order to do that he used ideas that we've come across in electric fields when he looked at Coulomb repulsion. In other words, the force between the two positive bits, the force between the positive nucleus and the positive alpha particle. As we know from electric fields, that is a repulsive force, and that leads on to the diagram that you can see on the screen. Now we know that the alpha particles were scattered at different angles. We're not going to look at all of the different angles because the physics there becomes extremely complicated and is really a degree level way of looking at it. What we're going to be focusing on today is what happens with the particles that are pretty much backscattered. So in order to look at this then, we're going to look at a closest approach method. We're going to take the alpha particle and the gold nucleus, and we're going to say that the alpha particle pretty much collides or approaches head on with the gold nucleus. At this point we are interested in how far this closest approach position is from the gold nucleus. Now to determine that we need to know two things. Firstly, we need to know how much kinetic energy the alpha particle has when it is fired from the source towards the gold nucleus. When it gets to this point here, we're going to assume that the velocity of that alpha particle becomes zero. All of the kinetic energy has been transferred into potential energy. By studying the equations for kinetic energy and potential energy, we can therefore have a look at what this distance is between the alpha particle and the gold nucleus itself. From electric fields then, we know, and we have the equation, that the potential energy is Q1 Q2 over 4 pi epsilon naught r. Now remember that being potential energy, it's just r on the bottom, it's not r squared on the bottom. When we get to the point of closest approach, all of the kinetic energy then has been transferred into potential energy. We can therefore say that the initial kinetic energy of the alpha particle, so that's the energy when it was emitted from the source, will equal the potential energy when it reaches the point of closest approach. So the kinetic energy at that point there must equal the potential energy at that point there. That comes from everything that we've studied about conservation of energy in year one, and obviously even going back as far as GCSE. So in order to have a look at some typical values then, let me just work you through an example. A typical value for the kinetic energy of an alpha particle would be somewhere around about 5 mega electron volts. So let's use 5 mega electron volts and let's work it through the equations to show you and to get an estimate at least for the radius of this gold particle, this gold nucleus. Firstly then, for kinetic energy, we've got 5 mega electron volts, so that's 5 times 10 to the 6, but obviously we need to convert that into joules by multiplying by 1.6 times 10 to the minus 19. That will equal the potential energy, which is given by the equation in red just above what I'm writing. Let's start to substitute some numbers in then. So for the charges, firstly we've got the charge of the alpha particle, which will be 2 times E, the fundamental charge, 1.6 times 10 to the minus 19. We need to multiply that by the charge of the gold nucleus. Gold then has a proton number of 79, and then obviously we need to multiply that by 1.6 times 10 to the minus 19 again. We're now going to divide that by all of our constants, 4 pi times epsilon naught, which is 8.85 times 10 to the minus 12, and that is multiplied by r. Now we will obviously be doing a little bit of rearranging. We'll be multiplying both sides by r, and we'll be dividing both sides by everything we've got on the left hand side. First though, we notice that we can do a little bit of cancellation here. We can cancel this 1.6 times 10 to the minus 19 with one of these on the right hand side, because obviously E is 1.6 times 10 to the minus 19 as well. Let's rearrange that. What we end up with, let's change colour to blue as well, is R is equal to 2 times 79 times 1.6 times 10 to the minus 19, and we're going to divide that by 4 pi times epsilon naught 8.85 times 10 to the minus 12 multiplied by 5 times 10 to the 6. When we work that through, then what we're left with is a radius of 4.5 times 10 to the minus 14 of a metre. Now that's in roughly the right order of magnitude that we're expecting. Somewhere around femtometers or something like that is what we know and what we should expect for nuclear radius. So for Rutherford's idea of measuring nuclear radius, that was a good enough estimate, but unfortunately in that methodology there are a couple of limitations. The main limitation that we care about is the fact that when we're dealing with that Coulomb repulsion, firstly we're measuring the distance from the centre of the two particles. So we're measuring that distance there. We've got a couple of different sources of error therefore in this method. Firstly, we have an error in the radius of the alpha particle. Now the radius of the alpha particle compared to the radius of the gold nucleus is quite small, so that error will be small. But if we tried this methodology with smaller nuclei, if we tried to take it down to something like carbon by using graphite or something like that, then that error would become larger. The second error we've got is that actually the two particles do not touch. If they were to touch and if they were to get within the range of the strong force, then that alpha particle would, getting close enough, be absorbed and we wouldn't be able to measure it. So we now have two sources of error. What we're trying to measure is the radius that I've drawn there in black, but we have two sources of error. Firstly, we have the fact that those two particles don't touch, shown in green, and secondly we have the radius of the alpha particle as well, shown in red. So therefore the closest approach methodology does have its limitations, and we can only therefore get an estimate of what the nuclear radius is. Therefore we need a better method, we need a more accurate method of trying to measure nuclear radius. So in order to get a better estimate of nuclear radius, we need to move on to look at using electron diffraction. Now, just to give you the historical context here, Rutherford's experiment was at the turn of the 20th century. The idea about wave-particle duality from de Broglie didn't really come about until the 1920s, the early 1920s. So Rutherford had no chance of using and no knowledge of electron diffraction in order to use that to try to measure nuclear radius. And these electron diffraction experiments didn't really come about until the late 1920s and into the 1930s. What we're doing then is we're using the idea that electrons can behave as waves, and that part of our wave-particle duality. Now, obviously, if we were in school, I would be showing you the electron diffraction experiment, but unfortunately, obviously, at the moment, we're just going to have to do with a diagram, and I'll try and talk you through as best I can. Let's have a look at the apparatus then. Firstly, we have an electron gun. The electron gun will emit electrons. They will normally then be accelerated through a potential difference in order to allow them to gain energy. That will then be directed at a graphite screen. Obviously, the graphite screen then acts as a diffraction grating. So again, I'd expect you to be going back into the year 1 topics and to have a look at how diffraction gratings work. That will then give us some kind of diffraction pattern, and using a screen at the end of the diffraction tube, we will be able to see a diffraction pattern. Now, if we were to look end on, so if we were to look in this direction at the diffraction tube, then on the picture on the right hand side, that's the diffraction pattern that we would see. So in order to understand the diffraction pattern from the electrons that we see, we need to remind ourselves of how the diffraction pattern for light works. There are a couple of subtle differences, but we'll talk about that in a moment. We'll focus right now on the similarities between the two. Now, for both of these patterns, firstly, we can see that in the middle, we do have a large bright central fringe, a high intensity central fringe. That then decreases before we have outer fringes, equidistant on each side, so we have outer fringes in both patterns. Now, the subtle difference between the electron diffraction pattern and the light diffraction pattern comes in the minima. When we look at a similar graph for the intensity of the diffracted electrons as a function of diffraction angle, we can see the similarities then on the graph. We can see that we have obviously 0 degrees, we have our large intensity central fringe there. We obviously have an outer fringe here. But one of the key things that we can see is that the intensity at the minimum doesn't actually get to 0. As the angle increases, in general, the intensity is going to decrease, but we do, of course, have the minimum. Now, how this would then carry on is you'd probably have another fringe there, and a couple more minima, but we're not really interested in these outer fringes. What we're interested in order to try to calculate a nuclear radius, is the position of the first minimum. So moving on to a fresh slide then, what we need to know, what we need to use in order to calculate a nuclear radius is this angle here, which is called theta min, and that is the angle of the first minimum in the electron diffraction pattern. Now, without going into the theory too much again, because obviously when we start to get into the real deep theory behind wave-particle duality, we're into some pretty high-level degree level theory there. But we can use all of our theory to get that the radius of the nucleus is 0.61 lambda divided by sine of that angle of the first minimum. Now, the wavelength that we're talking about here is the wavelength of the electron. Now, obviously, because we're talking about wavelength of the electron, we can now see that we are talking about electrons behaving as waves, and that part of wave-particle duality. Now, in order to calculate that wavelength, we're going to use the equation E is equal to hc over lambda, where h is Planck's constant, c is the speed of light, and E is the energy of the electron. Now, in order for this experiment to give us the results that we want, the wavelength, and ideally the wavelength of the electrons, needs to be of roughly the same order of magnitude as the radius of the nuclei. We can see from E is equal to hc over lambda that as we increase the energy of the electrons, we're going to decrease the wavelength of the electrons as well. We can see that E is proportional to 1 over lambda. Higher energy is going to give us a smaller wavelength. Now, in order to get the wavelength small enough and to get roughly the same order of magnitude, we obviously therefore need very high energy electrons. From the Rutherford experiment discussion that we had a few slides ago, we know that the order of magnitude that Rutherford was getting was around about 10 to the minus 14 of a metre, and we can see that maybe we're going to get down to, of the order of femtometers, 10 to the minus 15 of a metre. Let's just use 10 to the minus 14 of a metre now then, and say that if we wanted a wavelength of 1 times 10 to the minus 14 metres. Well, what energy of electron do we need to get that small a wavelength? So if we plug numbers into the equation, then E is equal to hc over lambda, so Planck's constant 6.63 times 10 to the minus 34 multiplied by the speed of light, 3 times 10 to the 8, and we're going to divide that by the wavelength, or at least the order of magnitude of wavelength that we're looking at, which is 10 to the minus 14 of a metre. What that gives us in joules is 1.99 times 10 to the minus 11 joules. Now obviously that's all right from a joules point of view, but we're going to want to convert that into electron volts. And in mega electron volts, if we divide by 1.6 times 10 to the minus 19, that gives us an answer of 124 mega electron volts. Now, what that's saying is 124 mega electron volts, so that's of the order of 10 to the 8 electron volts. Now, if we remember back to last year, in order to get an electron with an energy of 10 to the 8 electron volts, it needs to be accelerated through a potential difference of 10 to the 8 volts. Now, 10 to the 8 volts is extremely high voltage. If we were doing the electron diffraction experiment in the lab, then we would only be able, really, from a safety point of view, to go up to an order of kilovolts. In order to get these electrons down to the wavelengths that we really need, we need to go from kilovolts up to 10 to the 8 volts. So we're looking at another 5 orders of magnitude there. Obviously, if we want to get even smaller, we need smaller from the wavelength point of view, we really do need to increase that energy, and therefore we need to be going from megavolts from the potential difference. Really, if we're being honest, the closer we can get to gigavolts to really get that wavelength down to femtometers, we're starting to talk about some pretty hefty potential differences that we need to accelerate our electrons through. But hopefully that will just give you an idea of the orders of magnitude that we're looking at. In order to get a radius, in order to study a radius of roughly 10 to the minus 14 metres, we need a wavelength of, again, roughly 10 to the minus 14 metres. And therefore we need electron energies in the order of magnitude of hundreds of electron volts. So here is your question for this lesson then. A sample has an electron beam directed at it in order to determine the radius of the nuclei in the sample. The electrons in the beam are accelerated through a potential difference of 560 megavolts. The resulting diffraction pattern has the first minimum at 17 degrees from the centre of the pattern. Calculate the radius of the nuclei in the sample. As usual, go away, work out an answer, pause the video and come back when you think that you're happy with the answer that you've got. So in order to calculate the radius then, we're going to take the equation r is equal to 0.61 lambda over sine theta. Theta here is given in the question, 17 degrees. We do need to work out lambda though. Lambda comes from E is equal to hc over lambda. If we rearrange that, lambda is equal to hc over E. Combining all of that together then, our radius will be 0.61 multiplied by hc divided by E multiplied by sine theta. Now in order to calculate E, we've got the acceleration potential, so we've got 560 mega electron volts, so 560 times 10 to the 6, sorry, times 10 to the 6, not times 10 to the minus 6. And we need to multiply that by 1.6 times 10 to the minus 19 to go from the definition of electron volts and to convert that into joules. Obviously, remember at this point, if you have been doing circular motion work or something like that, make sure that for theta your calculator is set to degrees before you plug this in. Once we put all of that into our calculators, then we end up with a radius of 4.63 times 10 to the minus 15 meters, or I would write that as 4.63 femtometers. And again, at that point we can sanity check our answer. We know we're expecting something of the order of femtometers for the order of magnitude of the radius, so at 4.63 femtometers we're quite happy with that answer. So to summarise then, today we've looked at how to determine, using a couple of different experiments, the radius of a nucleus. The first experiment we looked at was from Rutherford's experiment and was obviously just a different approach to Rutherford's experiment, and we said that the kinetic energy of the alpha particle at closest approach will equal the potential energy, assuming that that alpha particle comes to a rest. And remember that from our electric fields topic, potential energy between two charges is Q1 Q2 over 4 pi epsilon naught r. From that methodology we also just discussed briefly the limitations on that. We then moved on to have a look at electron diffraction, and we had the equation R is equal to 0.61 lambda over sine theta, where lambda is the wavelength of an electron and can be determined using E is equal to hc over lambda. Theta was the angle of the first minimum on a graph of intensity of our diffracted electrons against the angle of diffraction. So that's it for this lesson. As usual, any questions please let me know, and I'll see you next lesson.